Lesson 7.5. We're going to get going on that. Lesson 7.5. The first thing I'm going to do is come over to our Google Classroom. I'm going to open up just a couple documents. Today we will use the Desmos pre-programmed graph, so I'd recommend you go ahead and click that. I'm going to have quite a few where today is the lesson itself is built on using graphing tools. So you need to open this up. Even if you prefer algebra, you still need to open this up for today. And not only that, I'm going to be using the formula chart exclusively on the bell ringer. I will use the formula chart, that is to say. So on the bell ringer, we got 3 problems here. We're going to be talking about writing an equation because that's really what the TEKS say that the pre-calculus student will be able to do is graph these different shapes given key attributes or characteristics. So number 1 here. We'll take a look. It says write the equation of a parabola. So that's what I'm going to do here. Write the equation of a parabola. So I'm going to first draw your attention to on the formula chart that for the parabola, let me find that parabola. Here it is. And really all 4 shapes here, circles, parabolas, ellipse, hyperbolas, the formula, whether you're looking at the horizontal or the vertical formula all the way down your list, the only thing that's different on any of the formulas is where the y minus k and the x minus h are located. That's the only thing that will change position with one another. Everything else is basic. So what I'm going to do here is to copy down what I know is true of a parabola. And that's you'll have a parenthesis squared equals 4p times another parenthesis. As we've learned the last few classes, what's required of you to solve one of these problems from here is knowing your vocabulary and just plotting the few points that they give us. Actually, this one, they don't even give us, they gave us 1 point, but not multiple. So I'm actually not going to do that on this problem. It says here, the directrix is x equals 4. So again, if you wanted to see where that would be, that's on the x-axis, 4 units to the right, and it would be a vertical line. So you'd go 4 units to the right, and you'd have a vertical line. That's what that would look like. But you actually don't need to do that on this particular problem, but there it is anyways. What could I do? Well, if I go to the formula chart and I see directrix here, notice I have 2 different formulas for directrix. I have x equals a value and y equals that same value. Well, no, I'm sorry. H and k are separate, but we have x equals something or y equals something. On our problem, what were we given? X equals 4. What that means is that we're using the formulas that are on the left side. So now I know where y minus k is located and the x minus h. So y minus k is located here and x minus h is located there. We also can establish that even though our problem said that the directrix is x equals 4, the formula chart said that x would equal, for the directrix, x would equal h minus p. I'm going to write that down here for a second. Now we're also given this focus value. It says the focus is located at -2, -5. So that would be left 2, down 5. 1, 2, 3, 4, 5. And so this would be my focus. So if you wanted to, you could start solving things going off the distance change from here to here, that's 6 units. We can find out that the vertex would be halfway through there, so on and so forth. So you could use the graph if you wanted to. On this one, you could also use algebra because focus is one of the values that's listed on the formula chart. So you can actually just use you don't even have to use your distances and spatial awareness to solve this problem. You could actually just solve it saying, okay, the focus is h plus p, comma k. So h plus p comma k is what I'm going to write down next. H plus p comma k. This is the formula chart right here. This is what they gave us, the given. And so what I can determine from here is that number 1, -5 is my k value. So when I go to substitute this in, I would have y minus, I take out k and replace it with a -5. So it's y minus a -5. Is there a cleaner way of writing y minus a -5? Yeah, I could just say that's y plus 5. And then I can see that 4 equals h minus p if I do a substitution there. If x is 4, I can just plug the 4 right there. So 4 equals h minus p. I can also say that negative 2 equals h plus p. I can solve this using the old algebra technique called elimination. If I combine these two equations together, we can find out that 4 minus 2 is 2. So 2 would equal h plus h is 2 h's. Negative p plus a positive p. Eliminate each other. So 2 equals 2h. And if I want to isolate that h from my formula, that 2 is multiplying. What is the opposite operation of multiplying by 2?
Dividing.
We could divide by 2. And we could find out, okay, h is equal to 2 divided by 2, which is 1. So now I can come up and substitute that in. So this h gets removed, and in its place is a 1. Now, when you look at these points, you'll notice why we say so frequently inside lies. It's because we have the location of the vertex being a right 1 unit, but when we put it again into the parentheses, it looks like x minus 1. It looks like a lie. So that's why we say that. We're left with one thing left to do. We need to solve for p. I would suggest pulling either one of these two equations to solve for p. Now that we know h, we just plug it in. I'll take this bottom one right here. I think this one would be the easiest personally. And so I'm going to say, instead of h, I'll say 1 plus p. So negative 2 is 1 plus p. How do I isolate this p? We subtract 1. And so 2 minus 1, excuse me, negative 2 minus 1 is negative 3. So negative 3 equals p. That's what I was talking about, that the focus is 3 units away. And the reason it's negative is because this graph would open around our focus this direction where it opens left. So the p is negative, meaning it's opening to the left. 3 either way. That's visually what that meant. The formula wants 4p. So what would be 4 times that negative 3? What would that equal? Negative 12. And that would be the answer to number 1. Quick review. If you want to draw this perfectly accurate, the width here, if you're wondering why does the equation have 4p? Well, mathematically, that's the way it works out. But as it turns out, there's something else special about this. The distance across the focus here is called the lattice rectum. That length is always the absolute value of that number. So if you drew it perfectly, this would need to be 12 units wide. Isn't that neat? So that would have to be 12 units wide if it was drawn perfectly. So I don't think I drew mine accurately. I think it would need to be much wider to get it to be, it need to be 6 up and 6 down from that focus to get it right. All right, part 2. It says, write an equation of an ellipse. So I'm going to pause and do the same thing I did first on the last problem. So to write an equation, I'm going to copy down what is common in both ellipse formulas, both the horizontal and the vertical, which happens to be everything but the x minus h's and the y minus k. Everything else is the same. So what did the formula look like? It was a parenthesis squared divided by a squared plus another parenthesis squared divided by b squared, all that equaling 1. The part that alternates is this equation going to have, excuse me, this fraction going to have the x minus h in the numerator, and this one have the y minus k, or is it going to be vice versa? That's the part that alternates. So to determine that, we need to know some vocabulary. It's going to say covertices. What should we associate covertices with? It's either 2a, 2b, or 2c. 2b is correct. It's 2b. So the other words for covertices from on an ellipse, the minor axis goes from covertice to covertice, or covertex to covertex. So you could call that 2b. And if it were a hyperbola, you would call that the conjugate axis. So those are other words that mean you would solve the same way. So if I pull out a graph real quick, if we went left 1, down 3, left 1, down 3, we would have this point here. That's a covertex. And it says left 5 down 3. Left 1, 2, 3, 4, 5 down 3. There's my other covertex. Great, there's my points. To solve this, we would need to calculate the distance between these 2 points. So this covertex is left 1 unit. This covertex is left 5 units, but we only want the distance between them. So what's the difference between being left 1 and being left 5? How many units apart are those? 4. They're 4 units apart. That means 2b equals 4. Now something that's very important about this is we are connecting that our covertices deal with the letter b, just like this fraction here deals with the letter with b squared. Since this is moving left and right along the x-axis, left and right, that means my parentheses in the numerator is going to have the x minus h on this one. Why? Because it's moving left and right here, and these 2 points move left and right of one another, horizontal. And so the b, since they're connected with the variable b, and the b fraction, I call it the b fraction as the b squared, I need to move it horizontally. That means the x minus h. That leaves us with y minus k over here. Are you okay with what I've done there? How I made that observation? Okay, so now let's find the center. If 2b equals 4, to find the center, let's solve for 1b. What does 1b equal? 1b would equal 2, and you could plug this in. B squared would have to equal 4. I'm going to go back to that 1b in a second here. If 1b equals 2, that means the center is 2 units away. So I'm going to go to the middle. It's 1, 2, right there. That's our center location. It would be left 3, down 3. Left 3, down 3 would be the center. Left 3, down 3. So we can plug those in. Again, they're going to look like lies because it's going to be a minus a negative 3 and a minus a negative 3. So it's going to turn into a positive 3 and a positive 3. So now we have all that done just off the covertices. So we come back and say, all right, this problem has foci. What's the formula for foci? 2a, 2b, or 2c? This is 2c. So left 2, left 3, up 2. Here's a foci. And left 3, down 8. So 4, 5, 6, 7, 8. Here's my other foci. Down 8. This foci is 2 units up. This one is 8 units down. We're doing total distance. So 2 plus 8 is how many? 2 plus 8 is 10. And if we solve for c, we would find out that c equals 5. Okay, now that doesn't go in the equation, but what it could do, if you didn't already know it, it could find the center for you, that the center is 5 units away. Notice that negative 3 plus 5, negative 8 plus 5 is negative 3, so they are 5 units apart. But I do have another formula on the ellipse. It's called the ABC relationship, that c squared equals a squared minus b squared. So let's write that down and solve. C squared has to equal a squared minus b squared. We're going to use our values. If c is 5, then c squared equals 25. So we'll say 25 equals our unknown a squared minus the b squared, which is 4. B squared we know is 4. I do my algebra, I'll add 1, and we find our a squared that we've been looking for. 29 equals a squared. So that would go here and be our solution to number 2. This parabola, or this, ellipse, if we were to draw it, what it would look like is it would be a little bit taller than the foci, and it would go from these points in here. So it looks something like that, give or take. Foci being the reflection points. All right, and now Number 3, it says write an equation. So here we are writing an equation again of a hyperbola. So I'm going to go to the formula chart and take the standard form. And again, everything but the y minus k's and the x minus h is what I'm copying. So I should have on the first fraction a parenthesis squared over a squared minus another squared over b squared equals 1. On this particular problem, they give me vertices. I'm going to stop. Vertices. What vocabulary term should you associate with vertices? 2a, 2b, or 2c? Vertices are 2a. So 2a are at 0, 0, the origin. That's a vertice. And 0, 4, 2, 3, 4. There's my other vertice. Okay, so 2a, let's make this connection in our brains. 2a is moving vertically. That means for the equation, the a part, the a portion, the a fraction is going to move vertically. So this needs the y minus k. This fraction needs the x minus h, because it's the a value that's moving vertically. We could count the distance. This is the distance from 0 to 4. So how many units apart are they? 4. So 2a equals 4. What does 1a equal? 1a equals 2. We'll use that for the center. For the formula, we need to know that a squared would be 4. So a squared is 4. Okay, for the center will be 2 units either way from these vertices. So this is the center, and its location would be 0, 2. When you plug those in, remember inside lies. So it'll be the y will be minus 2 because we're going up 2. The x, or the h rather, will be a 0. Now let's think about this. I'm going to use different numbers for a second. What if this was 10 minus 0? What is 10 minus 0? 10. 5 minus 0? 5. What's x minus 0 going to be? X. So you could actually just clean this up and make it just say x squared. All right, the only thing left is this asymptote. Now, asymptotes are very helpful. They come from the formula chart. So if you go to the formula chart, the asymptote is shown in point slope form. What I want to show you is, if you note, one formula has b divided by a, the other one has a divided by b. You could check and say, okay, we're dealing with the equation that has y written as the front end of the first fraction, the positive fraction. So it's going to be a divided by b. Or you could think of it in terms of rise and run and say, okay, this is saying that my asymptotes are going to have a rise of 2 divided by a run of 3, if that makes sense. We already know that the y value was 2 squared. 2 squared. So that just means the b value here, let me write it the way the formula chart now shows you, is going to equal 3. So 3 squared would be 9. And this would be our equation. Now, I got to tell you one thing that can be a little confusing, though. Let's just pretend, for the sake of argument, that a was actually equal to 8 from right here. Let's say we had an a that equaled 8. And then you come to this part and it says a equals 2. What that would mean for the fraction is that the fraction would be reduced. So you might see that where we know a is 8, but then you see something where it says, and then we're looking for b, but you have something that says, well, it should be 2/3. What that would mean is it would be reduced and say, okay, what number, 8 divided by what gives you 2? 4. And so it'd be 3 times 4. You'd find out that the number would have to be 12 for b in that case. So I was just making that up on the fly, but I just want to point that out, that that will occur some points in time, okay? So with that, we have done our bell ringer, and it's time to start lesson 7.5. Let's take a look at what we're doing on lesson 7.5. Like I said, you'll need your calculators today, so don't be afraid of using, you can click, scan that link and it'll pull this up for you, your Desmos graphs. We are going to be using specifically calculators 22 and 23 today. Let's talk about this word parametric. We are looking at parametric equations. So chapter 7 is all about real world application. All your life, you have dealt with, I say you have, I'm assuming, many of you have dealt with watching some type of an athlete throw a ball, whether it's basketball, football, soccer, kicking a ball, baseball, whatever. You have someone throwing. That had wind resistance right there. Joke. Y'all are lame. Maybe my joke's just lame. There you go. That is what air resistance would do to it. But for our class, we're going to look at this. We call this shape a parabola. Now, all your life, you've just seen a full parabola graph. The truth is, in real world, when you watch someone throw a ball, do you actually see a blue line the whole way through where the ball went? Do you see that? No. Do you see a red line? Do you see a black line? No, you don't see a line at all. What you do see is just the ball moving along the path as it heads wherever it's going. That's all you see. But in math, what we've always noticed is the whole curve. That's because in math, we've always dealt with what's called the rectangular, the x and y's. We're going to add in a letter t, which deals with a parameter. Typically, I say typically because it's not always, the parameter is going to deal with time. And so I'll put in parentheses time. It doesn't have to be a time. It could be a theta. Why am I writing out theta? Let me give you a symbol. It could be a theta for like an angle, but typically it's going to be t for time. Orientation is going to refer to the direction in which it's moving. So the orientation of this drawing is that my ball is always moving rightward. It travels along this parabola moving rightward. It's always moving to the right. Goes up for a little bit, goes down, but it's always moving right. So we'd say it's moving to the right. That's orientation. This would be our parametric curve, the blue. All right. So that's what we're dealing with today. It's quite neat, actually. So how do we do so? How do we deal with this? Well, you're going to have to come up with an extra equation. If you have a third variable, we'll have to have an extra equation. So the way you're going to write these equations are no longer y equals x, or y equals mx plus b, y equals x squared, anything like that. What we're now going to have are two equations. We'll have the horizontal component, so the x equals portion, and we're going to have a vertical component. They call this g of t. So you'll have two different functions working together to make up this graph. Notice t, the parameter, is your independent, and now x and y are dependent variables. That's how it's written, where t is independent and x and y become dependent. This would be for your parametric equations. Notice they are, the word was plural, parametric equations, because there's two of them. And you'll have the variable time. And time is not usually unlimited. So we'll usually, that's why I call it parameter instead of a variable, because we'll look at it under a specific certain number of time. And again, it doesn't have to be time. I'm just going to call t time. It's just easier for me. And I think it'll make more sense to you to call it time. So how do we graph these? Well, I'm going to first show you technology, and then I'm going to show you algebra. So graphing these on Desmos, if you go to graph number 22, I have built parametric into Desmos here. So what you'll do is you'll take this x portion, your horizontal component of the graph, and type that into the x equation. So on ours, it's t squared minus 1. And when you do parametric, you must on Desmos use a t. Your y, or your vertical component, is going to be t divided by 4 plus 2. I'll zoom in so you can see this a little bit more. And they also gave us an interval of time. The time values they give us is -3 to 3. On the third line down, you need to make sure your interval goes from -3 to 3. Now watch what happens. When I change this 2 to a 3, my graph is going to extend. It's going to get longer because I've added time. Just as if I added 4 seconds or 5 seconds, or if I cut it to 0. You'll see that it changes how much graph you see. Now, one of the things I did for you to make life much easier is help you out with orientation and where an object would be in a certain particular point in time. I did that right down here. It says To check orientation, slide the value of u, this value u, positive, negative, and check the motion of the graph. So it's basically what I'm trying to say is from start to finish, you can see which way the graph moves. You see what just happened with that purple? This is the start on the left. This is the finish. Did you see the purple move on the graph? You can tell the orientation. This graph, it's not always moving left, nor is it always moving to the right, but it is always moving upward. And so you describe this orientation as being moved upward. That's the orientation of this graph. Now you'll see on their picture that they threw on time values. If you needed those, you would just type them in here. Say, okay, at -3, where's the location? And you would click the point, whoops. You click that purple dot and you say, oh, okay, that's at 8.125. Now they didn't list it on there, but if you needed to, that's how you would do this. If you're doing your homework on Alex and you need to know the object's position at any point in time, you could plug it in like that. Or for you algebra gurus, if you want to know at any point in time, you could plug it into your equation. So for example, this t equals 0, you could just plug it in. X equals 0 squared minus 1. So 0 squared is 0, minus 1 is -1. And over here, y equals, I'm just doing time of 0. Let me make this a little bit more clear. I'll say t equals here, t equals 0, t equals 0. If you solve this one, you would have 0 plus 2, y equals 2. What that means is this point right there is at the point left 1, comma 2. That's that point right there. I know it doesn't look like it on the graph, but on the x-axis it is counting by ones. On the y-axis it's not counting by ones, it's counting by twos. That's a 1, that's a 3. I should say it's counting by halves. So that means this spot right here would be the value of 2. Check it on my calculator. If you just typed in a 0, you would get the point -1, 2. So I just want to tie those two together. I'm going to get to what's the algebra for the equations, but that's for how you do it for time. All right, so I have a part B here. And I'm going to change the equations up a little bit. So we now have t squared divided by 4 minus 1. So I just add the little division by 4 underneath the t squared. And on the y equation, I'm going to change it to t divided by 5 plus 2. So very similar equations, slight changes. What does that do for my graph? Well, if I check the orientation from start to finish, it's still moving upward. That hasn't changed. My graph says, look at the time from -5 to +5. The parameters be -5 to 5. So I do that. If you check, the values won't always be the same. So like time 0 might be the same, which in this case it is. -1, comma 2. Time 0 is the same. But if you remember, we checked time -3 last class, or last problem, and we had like -8, comma 1.25. This time, it's no longer the same numbers. So changing the equations, though the graph might look similar, if I go back and forth between these graphs, they might look very similar. The time values could be completely different based upon the values we get. So I just plugged those in the calculator, and we found out that this value there was -1, comma 2. But this time, t equals 3, we discovered was 1.25, comma, what was it, 0.6, I think? 1.4. 1.4. Notice the difference between time equals -3 on this problem and time equal -3 on this problem. Quite a bit of difference. So the picture looked a lot like on Desmos. The time was totally different. You'll get used to that. These arrows talk about the orientation. This graph was always moving upward. It didn't always move to the left, it did not always move to the right, but it did always move upward. So that would be the orientation. So your first DOL, what I want you to do is I want you to use technology to graph this. And if you look at the graphs, you can eliminate based upon time equals 0. I want you to find the time equals 0 value. Will the time equals 0 value, is it going to be 6, comma -3? Will it be -6, comma -3? Will it be -12, comma -6? Or will it be -6, comma -3 here? Oh wait, I messed this one up. That's not -6, that's -3. Just realized that's two values that are the same. Sorry, let me get that one corrected. This is -3, comma -3. So I want you to graph these and check time equals 0. So that means you need to use this portion of my graph, time equals 0, and see which answer you get here. This would be DOL number 1. All right, example 2. So now let's look at the algebra. What if you wanted to graph these by hand without the graphing calculator? Well, rectangular form, like I was saying earlier, means it's in terms of x's and y's. You just think about it. A rectangle itself has 2 dimensions, length and width. And you could call, or if you looked at it, the length looks like an x value. The width here looks like a y value. So that's why they call it rectangular, because it's in terms of x's and y's. So if you wanted to graph, we would have to graph in terms of x's and y's, which means to graph this, you can't just use, well, you could, doing a lot of little points and doing connect the dots. But if you don't want to play connect the dots, what you have to do to graph this is eliminate your t, because we graph with an x-axis and y-axis. We graph in terms of x and y, not in terms of x, y, and t's. We don't have a t-axis. So how do we do that? Well, it's 3 steps. Here's the first step, is you're going to solve for the shared variable. There will be one adjustment to this if we have a trigonometric function, but until we get there, we solve for the shared variable, which on this problem, what's the variable that's shared? T. So what I'm going to do is solve for t, and I'm going to start with the x equation, because typically with rectangular, we end in y equals, and so I'm going to start with the x equation and end with the y equation. So I'm going to start with x equals t squared plus 2. And we're going to solve for the shared variable t, which means isolate the t. How do I get rid of the plus 2 here? You subtract 2. So I'll have x minus 2 equals t squared. The second question, how do you isolate t if it's being squared? What is the opposite operation? Least square root. Now, whenever you add a square root that's not originally there, it needs to come with a plus or minus, unless you know for a fact that it's going to be either positive or negative. We don't on this. So I'm going to put plus or minus. So we just found out that t equals plus or minus the square root of x minus 2. That's step 1. Step 2 is to substitute into the other equation. So substitute. That's substitute. I forgot the UTE. There you go. Substitute into the other equation. And so I'm going to copy this down. We start with y equals 2t. But instead of the t, I'm going to substitute what we know is true about t. T is equal to plus or minus square root of x minus 2. Step 3 is to simplify. So to simplify this, I would need to distribute the 2 through, and you can't distribute into a square root, but you can distribute the 2, it's multiplying, so I could write it as 2 square roots of x minus 2. And this right here would be my rectangular form of my equation. So when I go to graph this by hand, a square root is, if you've forgotten, the parent function of square root kind of looks like this. It curves up and to the right. And if we follow our rules, inside lies, so this would tell me go 2 units right. And then you would have your graph going this way that's vertically stretched by a factor of 2. So what that really means is if I started at that point here, a square root, you'd ask yourself for every unit you go over, you take the square root. So if I go 1 over, I would take the square root. Square root of 1 is 1, so I'd go up 1 over 1. Well, this is vertically stretched by a factor of 2, so you'd actually have this point here. And then if you went 4 units over, 1, 2, 3, 4, square root of 4 is 2. That's when you go 2 units higher, but this gets doubled. So if I went 4 over, I should actually go 4 up. And so your curve is going to look something like this. That's how you would do this by hand. In the calculator, we could check our work. We had the x equation that was t squared plus 2. T squared plus 2. The y equation was 2t. There it is, parabola sideways. We believe the equation is going to be y equals the positive square root of 2, or a square root of x minus 2 rather, and also the negative of the same equation. So I'll put a negative here, copy it and put a negative. So you notice, do my graphs overlap one another? Do these graphs overlap? Yeah, so we did it correctly. So that is the equation. It looked like I just drew the positive form. We would also need the negative value as well. So there it is. Now I'm accurate. So that's how you would solve by hand to solve this. Now in your next DOL, I'm going to give you a little hint here. I don't like that I've written this as y equals 4t quantity squared, because this takes a lot longer than it has to. What I want you to know is a little shortcut here. If y equals 4t squared, that's equivalent to saying y equals the quantity 2t squared. You just think about it, 2t times 2t is equal to 4t squared. So I'm going to rewrite it like this and say, write y equals 2t squared and x equals 2t minus 4 in rectangular form. And I want you this time to solve for the shared 2t. Solve for the shared 2t to come up with your equation. Use algebra. You obviously can use graphing, but I would recommend you use algebra. Solve for the shared 2t. So don't solve for t, solve for the shared 2t. DOL number 2. All right, now let's talk about how we do domain restrictions. So same concept of what we've been working on, but we're going to do domain restrictions. So you might remember that in math, you are not allowed to take the square root of a negative number, which means for this problem, time could not be less than -1. Otherwise, you'd be taking the square root of a negative number. Also, time cannot equal 0 because you'd be dividing by 0. So there's a couple things that cannot happen here. Restrictions, just rules that I know of, is that t, as far as t goes, if you look at the restriction on t, t could not equal 0. That's true. And then t has got to be, this says greater than, it would be greater than or equal to -1 if you solve this, because the way I showed you earlier in the year is I said, okay, if you're dividing 2t cannot equal 0, and you would solve this equation. And I'm going to get to this actual problem in a second here. So it says t cannot equal 0. And then over here, you would have that for a square root, t plus 1 has got to be greater than or equal to 0, because it cannot be negative. That's the rules, cannot be negative. So you subtract 1 and find out that t has got to be greater than or equal to -1. So not only can it not equal 0, it's got to be greater than -1. Writing this now, switch from inequalities to interval, would be easier to say, well, basically you cannot be 0, but you got to be bigger than -1. So from, or equal to -1. So -1 to 0, but you cannot equal it, so it'd be a parenthesis, union 0 to infinity. Any of these numbers would be okay that are within there for t. This is all for t, but domain does not talk about t. It's talking about x's. So how are we going to solve this? Let's figure that out. Step 1, we're going to follow the same steps. We're going to solve for what is shared. So I'll say solve for shared. I'm still starting the same step. Solve for shared variable. So I'm going to take the x equation and say x equals square root t plus 1. So how do I get rid of a square root? I didn't even ask you, what variable is shared? T. So I'm solving for the t here. How do I get rid of a square root?
Squared.
We square it. And so we will have x squared equals t plus 1. Now, what do I do here to get rid of this positive 1?
Subtract.
Subtract 1. And so we find out that t, well, let me rewrite this, that x squared minus 1 equals t. And that's what t equals. Now, we can come back over here for a second and determine that. momentarily, but for now, I'm going to continue on. So we continue on here, and step 2 was we substitute. So we're going to substitute now this shared variable. So the equation is y equals 1 over 2t. And so we'll replace t with x squared minus 1. And step 3 is to simplify. This problem is pretty easy to simplify. All you have to do is multiply a 2 through. So we'll have 2x squared minus 2. So there's our equation right there. That's our rectangular form. Y equals 2x squared minus 2. And you can see from this graph, again, you cannot divide by 0. So we'll have problems if there's a certain variable or certain value that we can get a 0 down the denominator. And you could solve that on their own, but you're not going to have that square root. That square root's been removed. So what do I do to actually get the full restriction? Well, if I started with these two values, said, okay, t cannot equal 0, and t has got to be greater than or equal to -1. But if I use this equation here, where I knew what t was in terms of x, and a reason why in terms of x is because I'm looking for domain, I could solve the restrictions. So here, t cannot equal 0. I'm going to substitute and say for the restriction here, and I say restrictions because there was 2 of them. Instead of saying t cannot equal 0, I could say x squared minus 1 cannot equal 0. So I substitute there. So the restrictions we had before is that t cannot equal 0 and t has got to be greater than or equal to -1. And I'm just substituting here. And so if I added 1 to both sides, we find out that x squared cannot equal 1, and then you would take a square root. And you need to add the plus or minus here. And so we'd find out x cannot equal positive or -1. Now we also have a second restriction. And I will substitute in for t. We know that t is x squared minus 1. So I'll say x squared minus 1 has got to be greater than or equal to -1. And so if I added 1 to both sides, x squared has to be greater than or equal to 0. We take a square root. And we just found out that x, and this would be plus or minus, but 0 is simply signless. It's just 0. So x has got to be greater than or equal to 0. So here's what this means. X cannot equal positive or -1, and x has to be greater than 0. Well, -1 is not an option because we have to be greater than or equal to 0. So if I wanted to write this in terms of interval notation, I would say I have to be greater than or equal to 0, but I cannot equal +1. So I'll do a parenthesis union 1 to infinity. When I look at the graph, that's going to be my restriction right here for the domain. Whoops, I should have included that up here. Let me put that up here. 0 to 1, 1 to infinity. Now you might be totally lost at what in the world did you just do there, Mr. Voorhees? But if you graph it, it's actually quite a bit easier to see this. That is true. If I come up and I graph my equations, here's the x equation was square root of t plus 1, square root t plus 1. And this is where we got that t has to be greater than or equal to -1 because you can't have a negative square root. And I also took 1 over 2t, 1 divided by 2t. And this is where we got that t could not equal 0 because you're not allowed to divide by 0. We had this graph there. I'm going to delete these from the previous problem. We have this graph. And if I change the time, you can see how this graph extends out. So there's my graph. And if I look at the domain here, I can check and see and say, oh, this graph does not go left of 0 and it doesn't equal 1. I have an infinite discontinuity there. And the graph is just totally undefined on the negative side. There's nothing there. So it appears to me that if we got our answer right here, let's graph this in green. Y equals 1 over 2x squared minus 2, that my graphs do in fact match on the right side. I just can't have the left side. And you could check the restriction. You would do the restriction. You would say that the first one was what? That x cannot equal, or let's just do this. X has got to be greater than or equal to 0. X greater than or equal to 0. And that will pretty well do the transformation for Desmos, but that's not the transformation, I'm sorry, the restriction. The problem with Desmos is it's programmed not to graph if there's an asymptote there. So it knows not to graph in the center, but truthfully, if you're going to write it all out, you would need to do the break at +1. You need to have that there is a break at +1 as well. And so I don't even know how to do cannot equals on Desmos. So I'm gonna just leave it like that. We got the correct answer with our restriction. It did not exist on the left side and it was broken at 1. What I would recommend for many students is just to graph them and look where the graph exists and where it doesn't. You could see easier than doing all this algebra that the graph was going to break at 1 and it wasn't going to exist on the negative side. So that's what this means, is that the smallest domain value of x is 0 and it travels on to 1 and it picks back up from 1 to infinity. But since it's a parenthesis, it does not equal 1. There it is in interval notation. Here they are in inequalities, except you don't need that -1 any longer, because again, the reason you don't have to say -1 right there is because this tells us x has to be greater than or equal to 0. So it can't equal +1, and x has got to be greater than or equal to 0. So that was kind of a lot there. I'm going to let you do one. It's going to be a lot easier if you just graph it and look at your restrictions from there. So that's what I would recommend for DOL number 3. Let's take a look at example 4. Example 4 is where we have trigonometry thrown in. So you will see this dealing with parametrics, because that theta is a third variable. So we've been dealing with theta for a long time, and that's angles that can be changed. So it is a third variable. And I realize up here that here on my Mac, I keep forgetting to save that. This problem right here, on a Mac, it doesn't take the theta. So I've been including it right there. There we go, as we've gone along. But for some reason, it throws it off from last year using a PC. So, okay, here we go. Write y equals 5 sine theta and x equals 3 cosine theta in rectangular form. So what do you do when you're not working with the t, you're working with the theta? It's actually going to be a little bit different because of the trigonometry. It's still 3 steps. So step 1 here. Instead of saying solve for shared variable, what I'm going to say is solve for trigonometric function, for trigonometric function. And I should say functions because usually there's 2 of them. So here we go. We have y equals 5 times sine of theta. What we're going to solve for on this one is sine theta. So how do I get rid of the 5 that's multiplying? How do I isolate the sine theta? We divide by 5. Okay, so we solve for one trigonometric function. Now let's do the same on the other. We have x equals 3 cosine theta. What do we do to solve for cosine theta? Divide by 3. Step 2. We're going to substitute into, you don't have to use this identity necessarily, but it's the easiest because it usually connects them, the Pythagorean identities. Substitute into Pythagorean identity. Now, on this particular problem, I was given a sine and a cosine. So when I go to my formula chart, I'm going to take the Pythagorean identity that has sine and cosine, which happens to be the very first one. Sine squared plus cosine squared equals 1. So that's what I'm going to copy down here. That's sine squared plus cosine squared theta equals 1. And I'm going to substitute into this. We have learned that sine theta is equal to y minus 5. So I can say that this sine squared is going to be equivalent to y minus 5, or it's not y minus, I'm sorry, y divided by 5 squared. If sine is y divided by 5, sine squared is y divided by 5 quantity squared. Cosine is equal to x divided by 3. So cosine squared will be x divided by 3 squared. So I just substituted what we learned from step 1. Step 3 is the same. It's just simplify. When I simplify here, I'm going to have y squared with a fraction squared. It's numerator times numerator, denominator times denominator. So it'll be y squared over 25 plus x squared divided by 9 equals 1. You might recognize that from the formula chart. This is the form of a vertical ellipse. That is a vertical ellipse right here. That's what this equation is right there. What does this mean? It's a vertical ellipse. It has no shift, so it'll be at the origin. You take the square root, we would go up and down 5 units. And we would go left and right 3 units. It's an ellipse because it's a positive. So there it is. Now I want you to notice this orientation. When you deal with trigonometry, you might remember me saying all year, sine is y, cosine is x. As long as they do sine with y, cosine with x, it'll work just like the unit circle. Check out these values. At time 0 or theta equals 0, you're on the positive x-axis. Up here, it's theta equals pi over 2, which is the same thing as 90 degrees, if you remember that. 90 degrees, 180 degrees is like pi, that's over on the left side. 3 pi over 2 or 270 degrees is down here, and 2 pi would make a full rotation. That is how the time would work. At the time, or rather the parameter theta would work. On my calculator, if you're going to use mine, the one thing that's tricky, is that you cannot use the theta. The way I've programmed it, you need to always use the t, otherwise it will not graph. So I'm going to do 3 cosine t and 5 sine t. So no thetas, just t's. There it is. There's your ellipse. I'm going to delete this one. We could check our answer, but I'm just going to tell you it's correct. And I'm going to go from 0 to 2 pi. 0 to 2 pi. And you'll see that's the full circle. If I did not go 0 to 2 pi, let's say I went to 3 pi divided by 2, you'd see it's not even the full circle any longer, because it would only go to there. So 2 pi would be the full circle, 0 to 2 pi, that's all you would need. And if you wanted to follow it on here, you could change these as well. 0 to 2 pi, 2 pi. And I'm going to go pi over 12 as my step. What that means is how much it'll change by. And so this right here would be pi over 4. Oh, excuse me, no. Pi over 6 is here. That's pi over 4. That's pi over 3. This isn't one of them. That's pi over 2, and so on. It would go all the way around like that. It might just be easier just to type them in and show you. So like at pi, you'd be right there. So I think it's kind of neat. Ties in the last 2 topics that we were just dealing with from chapter 7 and chapter 5. So it's kind of neat if you ask me. All right, you have a turn. I want you to graph this. Obviously, when you graph, you'll be able to eliminate either the vertical or the horizontal ellipse. You can eliminate one or the other. Then comes the orientation. You'll get your orientation. And if I didn't say that clearly, let me back up. For orientation, if you just look at the way it moves, you can tell which way the orientation is going. So in the problem I did, as this slider moves from left to right, is we move counterclockwise. And so my orientation, I didn't put it on there. Oh, there it is. It's moving counterclockwise. So when you do yours, you graph it, you can eliminate half the choices just by the shape. The other you can eliminate by the orientation. So DOL number 4. Let's look at example 5. So example 5, we're going to walk through, and I'm going to kind of give a spoiler here, that we might be dealing with the same equation over and over. Like this one, we're going to be looking at the rectangular equation, y equals x squared plus 2 for parts A, B, and C, all 3. But I'm going to change the parameter in these 3 examples. Since the rectangular function is the same, what that means is the graph will look the same. In terms of y and x, the graph will look the same. But what will be totally different might be where the time values are located and the orientation of the graph. So that's what I want to show you here. We're going to walk through the same 3 steps that we've been doing. So it says use this parameter to write the parametric equation that can represent this rectangular equation. Graph it and indicate speed and orientation. So step 1, whenever we do this, is, if you remember, solve for the shared variable. Solve for shared variable. There's no trig here, so I'm back to the solve for shared variable as my first step. So here in step 1, or in this example part A, what's the shared variable? X. So the first thing we're going to do is solve for x. So I have t equals x minus 1. How would I get x by itself here? Add 1. And you might have noticed I usually do the y equation last because typically our answer is going to be in terms of y. Either the parametric equation is going to be one of the two will be in y, or a rectangular it's in terms of y equals. So I usually take the equation that does not have a y. I start with that so I can finish with the y. So there's step 1. Step 2. I'm going to substitute this into the other equation. Substitute. So we take this y equals, and instead of an x, it'll be x squared plus 2. Instead of the x, I'm going to replace that with the parentheses and inside t plus 1. Now, truthfully, at this time, for calculator's purposes, you have your 2 parametric equations. You could graph this as t plus 1, x equals t plus 1, and y equals all of this right here. You could do that. What I'm going to do, though, is because on your homework, Alex is going to require you to do this, is simplify it. So if you were taking a test, you could just graph that and have your solution. But Alex is going to ask you to simplify this. And so to help us simplify it, I'm going to write that parenthesis twice, because that's what squaring means. Multiply it times itself. So I'll write it twice so we can multiply it times itself. And I'm going to use the foiling technique to help me out. FOIL, that stands for first times first, outside times last side, inside times inside, last times last. So t times t, that's my O. T times t is t squared. T times 1 is positive t. 1 times t is also 1t, or just a positive t. And then 1 times 1 is 1. I have a plus 2 on the outside. All this would simplify to become t squared plus 2t plus 3. I'm going to come over to my graph, and we'll see what this equation looks like. So I have x equation is t plus 1. Y equation is t squared plus 2t plus 3. I'm going to set the time being -10 and +10. So we get a parabola that's looking upward. Well, to check it, it should match the rectangular equation y equals x squared plus 2. So did we do the work correctly? Yep, we did the work correctly. Okay, so a little check here. I'm going to go from I'll just go from 0 to 5 here to make it easy. Let me go over here. And so as I move left to right, I'm going to take this off. 0 to 5, sorry. Doing time 0 to 5. As I go left to right, you can see which way the graph's moving. Let me go from -5, sorry. -5 to +5. So as I go left to right, you can see the graph moves to the rightward. Okay, so that's the orientation. And if you need a particular times, you could just say, where is it at 0? It's the value 1, 3. So on our picture, you'll see that time 0, this point right there, is located at 1, 3 is what the calculator said. And this graph was always moving to the right. Now, what I'm going to do on part B and C is I'm going to change up the parameter. The equation, the rectangular equation should still look the same, which means the graph should always look the same. But I'm going to change up the parameter, both B and C. So here we go. Let's try this again. Step 1 is we solve for shared. So I'm not going to write out all the step. I'm just going to say t equals 2x. The shared variable is x. So I need to solve for the x. How do I get x isolated? We divide by 2. And now we know x equals t divided by 2. So we have that part. All right, step 2. We substitute. So I'm going to take my other equation, and in the place of x, I'm going to replace it with a t plus 2 in that parenthesis. T divided by 2, I'm sorry, t divided by 2. Step 3, and by the way, for our calculator, you could just put step 2 right there, and that would graph just fine if you included that in parentheses. But step 3 is for Alex's sake. Let's simplify this. We get y equals, it's going to be t over 2 times t divided by 2 plus 2. When I simplify, I will have t squared over 4 plus 2. T squared over 4 plus 2. Those are my two equations. So I'll come over here and change what we had. Now again, the graph should look the same. It should end up looking like this green graph. So I have t divided by 2, t divided by 2, and I have t squared divided by 4 plus 2. Notice, do these graphs match again? So we still did it correctly. We have two totally different equations, produces the same rectangular graph. But what's different? Well, let's see. As I move left to right, it's still moving. So from start to finish on this, when I say left to right, I mean the slider. As I move the slider over, I see that the graph is moving left to right. So same orientation. But if I check time 0, you would see that time 0 is located in a different spot. That's not 0. 0. There we go. Time 0, it's at 0, 2. So this time, the orientation is the same, the times were different. This point right there was at 0, 2. That's time 0. So notice that's what changed. I'm going to show you one more of these. Let's look at part C. So again, the same final equation. So whatever happens, my graph should look like the green graph when I'm done here. Step 1 is to solve for what is shared. So we have t equals 2 minus x divided by 2. All right, this one's a little trickier to solve because a lot of people say, oh, I need to add 2 because they see this minus there. But the 2 is actually positive. So how do we get rid of, or how do we isolate the x if it has a positive 2 with it?
Subtract 2.
We subtract 2. So we have t minus 2 equals negative x divided by 2. Now I'm going to do a little 2 tricks in 1. Because I can eliminate this in 1 step, but it's 2 tricks. What's the opposite of dividing by 2? Multiplying by 2. But if we thought of this as being x divided by negative 2, you'd say, well, divide that, or multiply by negative 2, and that will get both of them. And that will still be the case here. So I'm going to multiply by negative 2 here. If I do that, these values simplify, and I'm left with negative 2t plus 4. So that's our x equation. Negative 2t plus 4. So I go to step 2. Step 2, I would plug that in here. So instead of, I forgot the equal sign, y equals, and instead of just the x squared, I want to say parentheses squared plus 2. Now, what is x equal to? Negative 2t plus 4. Negative 2t plus 4. Again, you could write that as your other equation. Step 3 says, let's simplify this. Color coordinate here. Step 3, color coordinate. All right, so y equals negative 2t plus 4 times negative 2t plus 4 plus 2. I'm going to FOIL this. So negative 2t times negative 2t is a positive 4t squared. Negative 2t times a positive 4 is a negative 8t. Positive 4 times a negative 2t is a negative 8t. And a positive 4 times a positive 4 is a positive 16. If we simplify this, we should get our solution. It'll be 4t squared minus 16t plus 16 plus 2 is plus 18. We should, when I graph these, get the same looking graph. It should look like the green graph. So negative 2t plus 4 and 4t squared minus 16t plus 18. Notice it looks just like the green graph all over again. Same graph. But what's different this time? If I check my orientation as I move this slider across, you'll see this graph is moving from the right to the left. It's moving leftward. So the orientation is backwards this time. And if I look for time equals 0, you'll see that this point happens to be way up here at 4,18. Time equals 0 is at 4,18. So it's in a totally different location. So I just wanted you to see that. I gave you 3 different examples where we got the same looking graph, but the orientation is different and the time is different. So that can happen. Yours, I'm not going to make you do this 3 times. I'm just going to ask you to solve this, and I'll give you a hint. If you do algebra as opposed to graphing, if you just solve this one right here, you will have your solution. If you solve for the same shared variable right here, if you notice your equations, you will have your solution. So do your algebra, solve for x to get your answer here to DOL number 5. All right, let's look at projectile motion. So projectile motion is where we apply this to real world. I started off with the illustration. What happens if we throw a ball and we want to monitor it? The way it works out, and this is, I'll call it physics. It's where math meets real world application. Technically, that is what physics is we've learned that the horizontal distance could be modeled by the amount of time that something's been in the air, times its velocity, times the cosine of the angle it launched at. Because cosine strips the vertical component and it gives us the horizontal component. Now for vertical position, it's not so easy because there's other factors. Now this is no wind resistance. That's very important I say that. This is for no other factors other than you still have time, velocity, the sine would be the y component. But then we have this second component come in and it has a g. What do you think g stands for? Gravity. Good. Gravity affects the vertical height of the object. So it's gravity times squared, if you're wondering that. If you just think about your values from physics, you always heard 9.8 meters per second squared. Second squared, time is squared. And then in feet, by the way, it'd be 32 feet per second squared. And then this h0 is your initial height. So if you're talking about you throw an object and you want to know horizontally what's happening, it doesn't matter if you throw it from the ground or from the top of a building. Horizontally, it's doing the same thing. Vertically makes a big difference. If I throw something from ground level versus if I throw something from the top of main building, the 3rd floor, vertically, that's a whole big difference. So that's where you include height. I have a calculator for this, and I'm pretty proud of this one. This one's pretty cool because I throw in a second little portion on there that I'll show you in a second. So when I pull it, it's graph number 23, projectile motion. And so walking through this problem here, it says Shane Leckler has a record, the career record for punting average with an average of 46.47 yards per punt. Suppose that he kicks a ball at initial height of 2 feet. So I'm going to write these variables out. Initial height of 2 feet. That means our initial height, h0, is 2 feet. With an initial velocity of 26 yards per second. So that's v0. 26 yards per second at an angle of 72 degrees. How far did the ball travel? Well, the key is you need to get units that are alike. And so for gravity, I'm not going to use 9.8 meters per second squared. I'm going to use that gravity is 32 feet per second squared. And only that, this 26 yards, I need to convert that, and I'm going to say it's actually going to be 3 times. Now, do you know why I'm saying 3 times 26? Because 1 yard equals 3 feet. And so that's my value I'm going to use here. If you use this set of equations here, we could solve this saying our initial velocity was 3 times 26, which is 78 feet per second. He kicked this ball at 72 degrees from initial height of 2 feet. We're going to use gravity as being 32. If you look at this, you could trace this value. You could trace where the ball is and see how far horizontally it goes when it hits the ground. Or something if you open up this folder here for the projectiles, not the projectiles attribute, sorry, the end results of the projectile, you can scroll through there and read these all on your own. But there's a point near the bottom where I say, the projectile at the maximum height and the projectile when it hits the ground. 2 things we solve for commonly. When it hits the ground, this tells us it's 112 point, I'm going to call it 4 feet. 112.4 feet. 112.4 feet. And this is roughly how far the ball travels. So I'll say squigglies. The ball travels approximately 112.4 feet. Now, the math getting into this is you would just have to solve these equations, that x would equal t times our initial velocity, which we got was 78, times the cosine of 78 degrees. You would solve for what is shared. You do the same 3 steps. You would take this, solve for what is shared, which means you would divide over the 78 times cosine of 78, and you would substitute that into your next equation. So this one would be t times 78 sine theta. By the way, these are on the formula charts. Minus 1/2, our gravity was 32, t squared, plus the initial height of 2. You would take 1, substitute it in to solve. Okay, you'd actually want the y height of 0, so you plug in a 0, substitute those in for t's, and that's how you can go about solving. It would take a while, but that's how you do the algebra. Here's your DOL number 6. I would suggest using the calculator. All right, let's take a look at how we might be tested on these type of questions. So what are the parametric parametric equations for the curve given by the parameter t equals 4x and the equation y equals 2x plus 1 quantity squared? So this is just like the problems we were working through earlier where I have 2 different equations and we want to write parametric equations for these. So what we need to do is step 1, solve for the shared variable. So I'll just put a 1 here, solve for shared. And so the shared variable is x. So I'm going to start with t equals 4x. And I will solve by x. Since this 4 is multiplying, I would need to divide by 4 to isolate the x. And so we come up with the idea that, the truth that x equals t divided by 4. And at that stage, we can come through here and eliminate a and c. Step 2 would say to substitute this into the other equation. So we would now have y equals, and we have a 2 and then another x, or another parentheses, what I need to use here. So I'll do t over 4, and then I'll continue on here with the plus 1 quantity squared. And as I'm looking at my answer choices, this looks nice. I don't have to distribute the whole thing out. I just need to multiply this out here. That would be 2t divided by 4, which happens to be half a t, t divided by 2. 2/4 t. 2t over 4 is the same thing as 1/2 t. So it'd be t over 2 plus 1 quantity squared. Looks like the answer will be D for this problem. And then finally down below it, says a baseball player swings and hits a baseball at initial height of 30 inches. So that would be your initial height. Let me go ahead and write that down. H0 equals 30 inches, which would in turn, by the way, be 30 divided, if you divide that by 12, you have 12 inches in 1 foot. This would be 30 over 12 feet. So we'll get to that in a second. I think that's going to be 2.5 feet, but we'll check that in a second. It says the ball travels off the bat at initial velocity. So here we go, initial velocity, V0 of 130 feet per second. And the angle is 25 degrees. So I'll have to write the theta over here, 25 degrees. The outfield wall is 400 feet away from the batter and the height of 10 feet. Will it be a home run? And so here's the idea. You have a baseball player who hits the ball, and that ball goes flying off the bat. And we want to know, way out here, you happen to have a fence. And we want to know what's going to happen between that ball and the fence. This distance is 400 feet. It says the fence has a height of 10 feet. We want to know what will happen to the top, the ball in regards to this fence here. That's what we're trying to figure out. Will it, it says, will it hit the ground before the wall? So will it fall and hit somewhere in here? Will it hit in the middle of the wall? It cannot be determined because it hits the very top point, or does the ball travel over the wall for a home run? That's what we wanted to determine. Well, using my calculator, how would we do this? I would first come over here to the projectile's attributes. And we say the initial velocity is 130 feet per second. The angle was 25 degrees. The initial height was 30 divided by 12, which is in fact 2.5. And gravity is 32 feet per second squared. Now, what I can do from here is I can go down to the end results. And so here's the picture. I know it's kind of zoomed funny here, but we want to see if the ball will travel over the fence. What we can do is this blue line represents the fence on my calculator. If we go to the end result, you can go into these values and say, all right, we want the fence to be horizontally 400 feet away. So I'm going to put a 400 there. And the height of this fence is 10 feet. When I type that in, you can see visually what's going to happen is that ball is going to hit the middle of the wall. So it's going, the correct answer here is going to be B. Now, let's say, and by the way, you can go through here. There's all different types of circumstances that like what is the height when the ball travels 400 feet? That's what we put in for X is 400. The height would be 4.6 feet. And the time that takes would be 3.4 seconds roughly if you rounded. And you can go all the way down and find these different values. Let's say you wanted to solve this by hand. You're like, well, how would I do that? Well, there's these formulas on the front side of our formula chart for projectile motion that I'm about to take and use and solve with. So the formulas we have is x equals t times initial velocity, which is, let me slide that over just a slight bit, times our initial velocity, which would be 130, times the cosine of 25 degrees. The y, let me slide the formula over a little bit more now. Okay, the y would be time times that 130 times the sine of 25 degrees minus 1/2 gravity, which because we're in feet, it would be 32 feet per second squared, plus the initial height, which we had was 2.5. Now, if you were wanting to solve this, what they gave us is a x value for the fence that's 400 feet away. And so I'm going to put a 400 here. And we're going to solve. And we want to know, is this value over here going to be greater than or equal to 10? Is how you would solve this by algebra. You want to know, would this value be, well, I should say greater than 10, because if it is equal to 10, C would be the correct answer. If the height, whenever this hits, is equal to 10, it could not be determined. If it was a negative number, A would be correct because that mean it would hit the ground before the fence. So negative would imply that if the ball went through the ground, it would hit the fence underground. That's what the negative would imply. If it hits in the middle wall, that means the answer would be somewhere between 0 and 10, and that's what we should get. If it was 10 exactly, C would be the correct answer, and D would be anything greater than 10. So this is how you would actually walk through it. And so I would solve this first equation, which I'm going to take this top right here and say that basically 400 will equal, no, I'm sorry, I'm going to solve this for t. I'm going to isolate the t. So we need to divide this. So 400 divided by 130 cosine of 25 degrees should equal our time. So I'll go back to my calculator. And as I'm going to show you, the value we're going to get for our answer is going to end up being this 4.6. But let's just check it out here. We're going to say that our time, and I'm just going to type it in like this, time will equal 400 divided by 130 cosine of 25 degrees. So that's how much time would take place. Notice that's the same value right there. So now that we know how much time it takes, the time for the ball to travel 400 feet, roughly 3.395. So I'll do approximately since I rounded. We would now take this and plug it into this equation for t. So we take that value and plug it in here. This is how you do it algebraically to try to get your answer. Whoops. And we will compare it to 10. For the answer to be a home run, again, it would have to be greater than 10. But we're going to find out it's greater than 0, but less than 10. So when I plug this in, now that we know what time is, I'll say time times that 130. So I'm plugging in this value right there. Since Desmos knows what time is, sine 25 minus 1/2. Let me make this bigger so you can see it. 1/2 times the gravity value of 32 feet per second squared. Oops, I need to make this time. There we go, time squared plus 2.5. And so we get the height 4.60568. That is how you would get where to go right here. The same height. That's the height of the ball when it hits the fence. So this ball would not travel over the fence. It would actually come down and hit there in the middle at 4.6 feet. So not exactly the middle, a little less than the middle, but that's how you do that by hand.